We're going to talk about titrations. So we have a titration cartoon picture here with the titrant, which is kind of this reddish rosy color inside a burette, which is the glassware we use to dispense the titrant. And then there's a flask below it, which contains a solution called the analyte. So in a titration, the analyte of unknown concentration is in a flask, and it is titrated with the titrant of known concentration in a burette. So the analyte is down here, the titrant is up here. In the lab that we do in Chem 102, the analyte is vinegar, and the purpose of the lab is to determine the concentration of acetic acid in vinegar. The titrant for our lab is sodium hydroxide. It is a very popular titrant. This is the reaction that occurs, the neutralization reaction between acetic acid and sodium hydroxide to form sodium acetate on the right and a molecule of water. Now, when the titrant added, the sodium hydroxide, exactly consumes the analyte so that there is no more analyte remaining and that there is no excess titrant that has been added, that is a point in the titration called the equivalence point. And this point is important because this is generally the reason that we use a titration. We generally perform a titration in order to determine the moles of unknown analyte. If we know the volume and concentration of titrant that's required to exactly consume the analyte, then we can determine how many moles of analyte were there in the first place because we have the balanced equation and we know how many moles of titrant we have added. The way that we identify the equivalence point is at a place called the actual end point. The end point is visible because we use an indicator in the analyte flask. The indicator in the lab that we did with the vinegar was phenolphthalein. It's a very common indicator that's used. It changes from being a colorless, from being colorless in an acidic solution to being slightly pale pink at a good end point, and then it becomes very bright fuchsia pink with excess titrant present. When the indicator changes color, that is what is called the end point of our titration. And the end point and the equivalence point are hopefully similar enough that we use them interchangeably in order to calculate moles of analyte present originally. Another aspect of titrations are titration curves. So if we monitor the titration by measuring the pH, as we add titrant from the burette to the beaker or flask that contains the analyte. So you can see the picture on the left if we were going to monitor the pH with a pH meter like you see, and you can see the bottom of the burette as it's dispensing titrant into the beaker. We can plot pH on the y-axis as a function of volume of titrant, on the x-axis. And this is what we're going to be talking about, which is the third point, and so on and so forth. And so each of these points represents answers you would get to part B of this calculation. And then those are plotted on the graph. Okay, so we're going to be talking a little bit more about titration curves. We're going to look into these calculations and how they plotted these values on the plot. So here's our strong acid, strong base titration, neutralization reaction at the top, the curve at the bottom. The strong acids always have a curve that looks like this. And as we mentioned before, the wording here, titration of the analyte is always whatever's listed here, and then the with implies that what follows is the titrant. So I've underlined the acid is the analyte, the green here I've underlined is the titrant, that's the sodium hydroxide. This is the initial concentration and volume of HCl in the flask that they start with. So 40 milliliters of 0.1 molar, that's where they get their initial number of moles of acid. So this point, each of these points that I'm highlighting with the blue dots, these are values on the table that correspond to the calculations that are done. So this volume and initial concentration, and then we're using 0.1 molar sodium hydroxide. They're the same concentration, and the one-to-one stoichiometry means that if we have 40 milliliters of analyte, we're going to need 40 milliliters of titrant. So it makes sense that the equivalence point is 40 milliliters. Now each of these values, each of these A through M represent calculations. This here in the middle, G, is our equivalence point. So we have several values before the equivalence point, and we have several values after the equivalence point. Before the equivalence point, hydrochloric acid is still present. After the equivalence point, you have excess sodium hydroxide that is present that determines the pH of the solution. So their table is based on this idea that you have some HCl still present early, and then after the equivalence point, you have excess hydroxide. That's why there are two parts of the table. So if we start with part A, if this is a strong acid, then all you have to do is calculate the pH using negative log of 0.10 molar, which is going to be the negative log of 10 to the minus 1, which is going to be 1. So that's where the first initial pH comes from. It's just the concentration of the HCl that we use. It's the same calculation you would do if I asked you to calculate the pH of a 0.1 molar HCl solution. That's how you would have done it. All of these values, B through F, that you're going to get, there's a neutralization reaction that occurs that changes the hydrochloric acid concentration. It depletes it. So you have to start with some initial amount, moles of HCl that you start with. And then, for example, part B, if we've added 10 milliliters of titrant, that's 10 milliliters of 0.1 molar, which is 0.001 moles, or 1 millimole, in the table at least, right? So 4 millimoles of HCl, 1 millimole of sodium hydroxide. These are going to react completely to completion until the limiting reactant is gone. Limiting reactant is the titrant, sodium hydroxide. That goes to 0, and we lose 1 millimole of HCl, which gives us 3 millimoles left over, which means when we calculate the concentration, when we calculate the pH, we need to know the concentration. So 0.003 moles divided by 0.050 liters. The volume has changed to 50 mils because we've added 10 mils of titrant to 40 mils of analyte. So we have a new volume, which is 50 mils. Our concentration gives a pH of 1.222, and that is this point down here on our graph here. That's point B. And remember, the first one was point A. Now if we move on, point C is here. That's after we've added 20 milliliters of titrant. That's here. So that's 0.002 moles of sodium hydroxide. That's 0.02 liters times 0.1 molar. It's still the limiting reactant, so it reacts completely, just like part B. That leaves 0.002 moles of hydrochloric acid, which means our pH is the negative log of 0.002 divided by the new volume, which is 0.06 liters, right? 40 plus 20 is 60 mils. So 0.0600 liters. And so the pH of that is going to be 1.477. And that is going to go back on our graph as point C. Point D, this volume represents 0.003 moles of sodium hydroxide, which is going to react completely and leave 0.001 or 1 millimole of HCl, which means the pH is the negative log of 0.001 divided by the new volume, which is going to be 30 mils plus 40 mils, which is 70 mils, or 0.070 liter. And that's going to give us a pH of 1.845. Now the pH is staying really low because we have a lot of strong acid still left over. So we've done point, and that's this point here, that's point D. We did point C in the last one. Point E is the next one. It's 39 mils, I think, right? And then point F is after that. We're getting really close to the equivalence point at point F. We're just 0.1 mil away. So point E, 0.039 liters times 0.1 molar. Here we're just calculating the moles of sodium hydroxide, which is still the limiting reactant. It's going to react completely, leaving 0. It's going to react with HCl, leaving just a little bit, 0.1 millimoles of HCl present, which means the pH is the negative log of 0.0001 divided by the new volume, which is 40 plus 39, or 79 milliliters. 0.079, there, we fixed it. So that's 2.89. 7, 6 with lots of sig figs, and that's the point on the graph, 2 points before the equivalence point. The point just before the equivalence point is where we're very, very close, and then the sodium hydroxide is still the limiting reactant. It reacts to 0, which leaves just 0.00001 mole. And then again, we calculate the pH by calculating the hydrogen ion concentration. pH is the negative log of the hydrogen ion concentration. 3.902 is the pH, or 3.903 depending on how you round 5. Now, at the equivalence point, if we look at the reaction, so here we are at the equivalence point. So let's see the moles at the equivalence point. We have 4 millimoles of analyte present originally. We have added 4 millimoles of sodium hydroxide titrant, which means they both go to 0. That is the definition of the equivalence point. Our products are the only thing that are left in the solution that remain in the flask. They are both neutral, right? Sodium chloride is a neutral salt. Water is neutral. They both have a pH of 7. So you know the pH at the equivalence point for a strong acid titrated with a strong base is 7. That will always be true if it's a strong acid being titrated with a strong base, or vice versa. Now these remaining ones are all after the equivalence point, which means that we have consumed all of the analyte and we have excess titrant left over. So your goal is really to figure out how much titrant is now in excess. The limiting reactant is now the analyte. So that means that our analyte goes to 0 and we have excess titrant. So now in order to figure out the concentration, we need to know the pH, we need to know the concentration of hydroxide. POH is the negative log of the hydroxide ion concentration, which is going to be 0.00001 moles divided by 0.0801 liter. That's the new volume, 80.1, which gives us a pH of 10.096. So you can see the pH increases very drastically right after the equivalence point. Another way to calculate pH is to convert hydroxide ion to hydrogen ion using Kw, and then pH is the negative log of the hydrogen ion concentration. Now the remaining calculations are exactly the same as part H. You just have to figure out how many moles of hydroxide you have added. And there it would tell you how many moles of hydroxide are in excess, which will tell you the hydroxide ion concentration, which will tell you the POH, which you can convert to pH. So for each of those, you have this is the moles of excess hydroxide that are shown. We're dividing by the new volume, which is 81 mils, 90 mils, 100 mils, 110 mils, and 120 mils, right? 80 plus 40. So you have to add the titrant and the analyte. And each of these, so point I gives you a pH of 11.092, point J 12.046, point K 12.301. So they're going to keep going up, of course. Point L, at 70 mils of titrant, we have a pH of 12.436. And then finally at point M, our last point, where we've added 80 mils of titrant, our pH is 12.523. So the pH kind of flattens out. And so those values are shown here at the top after the equivalence point. Point H, point I, point J, K, L, M, right? So we didn't do this in class. It's a rather tedious calculation, but it's shown here for your enjoyment, for your titration enjoyment. These values are all in the data on this data table. So remember there are two parts of the table because the top half of the table is before the equivalence point, the bottom half is after the equivalence point. They use millimoles again because it's easier than saying 1 millimole is easier to say than 0.001 mole. So changing the unit makes the number more normal in size so that you can just say 1 instead of 0.001. So here, this graph compares the titration of a weak acid with a strong acid. The weak acid is shown with the blue curve, and the strong acid is shown with the red curve. We looked at some calculations with strong acid. So the example for the strong acid, there's a neutralization reaction here shown, and the weak acid, the neutralization reaction is shown here in blue. So you can see the shapes of the curves are different. Liters, that is shown here right in the middle of that mark, right? And then after 20, right in the middle, and so on and so forth. So this table will also be used to match these data points after 10 mils, 20 mils, 30 mils has been added. At the equivalence point would be when 40 mils has been added, and then beyond the equivalence point is at the bottom when 50 mils and 60 mils of sodium hydroxide have been added. So here we're going to be looking at some calculations with weak acid titrations. So here we have our acetic acid and sodium hydroxide. The acetic acid is the analyte, and you can see these points here would be pH calculations that are shown in the book, or are at least discussed in the book. Points A through G, we're going to look at these. So that's point A, point B, point C, I've circled there. Point D, E, F, G. So those correspond to the points in the table and the points in the calculations. So before we add any titrant, that would just be the pH of 0.1 molar acetic acid. You would set up an ice table to determine the pH. It's 0.1 molar. You'd have 0 and 0 on the right, plus X and minus X. You'd set those equal to your K in your Ka expression. You would look up Ka on the table, and then you would solve for X. So this would be just like if I asked you to calculate the pH of a 0.1 molar acetic acid solution. You would get your algebra expression. You would find Ka in the table. It's right here at the top, 1.8 times 10 to the minus 5. And then you could either assume X is negligibly small compared to 0.1, or you could use the quadratic equation. Either way, you're going to get a similar value for X. Using the quadratic equation, it looks like we get 1.3 times 10 to the minus 3, 1.34 times 10 to the minus 3 if we assume X is negligibly small. And that gives us a pH of 2.88 either way. So that's going to be our data point in our table. Oh, 2.88 or 2.87, sorry. So that's going to be our value for part A. Part B, some of the acetic acid has been converted into acetate. This is our neutralization reaction that we're using. And so what that means is that we have created a mixture of a weak acid and its conjugate base, which is a buffer, right? And so whenever you have a mixture of a weak acid and its conjugate base, then you're going to use the Henderson-Hasselbalch equation in order to determine the pH. That's the fastest way to do it. So you're just going to figure out what concentrations you have after the neutralization reaction has occurred with the titrant and plug those values into the equation. So first figure out how much HA and A minus you have after the titrant neutralizes some of the analyte. So we have to start with our neutralization reaction from the titration. We have to calculate how many moles of titrant we've added. We have 10 mils and it's 0.1 molar. And we have to calculate our initial moles of acetic acid. 40 mils and 0.1 molar means we have 0.004 moles, which is the same as 4 millimoles. That's what your book has in the table. If we've added 10 mils of 0.1 molar sodium hydroxide, that's 1 millimole of sodium hydroxide, which will react to 0 to completion. It's the limiting reactant. If we have 0 initially of sodium acetate, and this reaction occurs all the way to completion, that means that we lose 0.001 moles of acetic acid, and we lose 0.001 moles of sodium hydroxide, so it's gone. That leaves 3 millimoles of acetic acid, and that means we go from 0 to 1 millimole of acetate. We're going to plug those values into the Henderson-Hasselbalch equation. The volume is 40 plus 10, which is 50 milliliters, which doesn't really matter in the equation because it cancels out anyway. pH equals pKa plus the log of the base is divided by the acid. The Ka is negative log of 1.8 times 10 to the minus 5, which is about 4.7447. Plug that into the equation. Concentration of A minus is going to be that 1 millimole that we calculated earlier, divided by the 50 milliliters, or 0.0500 liter. You could do 1 millimole divided by 50 milliliters. That would give you the same value, by the way. 3 millimoles divided by 50 milliliters is the same as 0.003 moles divided by 0.05 liters. So if we plug those numbers in, these volumes actually cancel, so they don't really matter. And that gives us a pH 4.7447 plus the log of 0.3333. That's going to subtract a little bit from our pKa. And that's going to give us 4.27 or 4.2676. That's going to be our point B on our graph. Point C is very similar, but point C is a special point called the midpoint. This is halfway to the equivalence point. And if we look at this more carefully, then we remember we start off with 4 millimoles of acetic acid, 0 millimoles of sodium acetate. If we have 2 millimoles of sodium hydroxide, that means that it reacts to completion to 0 millimoles. We lose half of our acetic acid and we gain 2 millimoles of sodium acetate on the right-hand side, which means our acid concentration and our base concentration are equal. What's important about having equal amounts of HA and A minus is that if we look at the Henderson-Hasselbalch equation, then when the A minus and HA are equal to each other, then the ratio is 1. And when the ratio is a 1, that means that the log of 1 is 0. If the log of 1 is 0, that means the pH equals the pKa. So this point on our titration curve is very important. You can use the titration curve, find the midpoint. The pH at that point will always be the pKa of your acid analyte. And we often use titration curves in order to determine that. So all we need to do is figure out the pKa, which is 4.74, and we know that that is the pH at the midpoint. And that's highlighted here on the graph. Now 40 milliliters, and that's halfway, right? So that's halfway volume-wise to the equivalence point. That's important. "30 milliliters is halfway between the midpoint and the equivalence point. At that point, we have added 3 millimoles of sodium hydroxide, which goes to 0, and our acetic acid goes to 1 millimole, and acetate is 3 millimoles. So we will again use the Henderson-Hasselbalch equation, plug those numbers in. The volumes end up canceling, and we end up with this ratio is what matters, which is a 3. And the log of 3 is 0.477, and so that's going to add some value to our pKa. The pH is 5.22, which is on the graph here. That's point D. Point E is our equivalence point. So with the equivalence point of the strong acid titration, the pH was 0. But at this point, at the equivalence point, we started off with 4 millimoles of acetic acid. The equivalence point means we have added exactly 4 millimoles of sodium hydroxide, which means that those both go to 0. And what we're left with is 4 millimoles of sodium acetate. The pH here will not be 0, however, because sodium acetate is a base. And so remember, acetate, all that's left in the flask at the equivalence point is sodium acetate. This is a basic salt. It is the conjugate base of a weak acid, acetic acid. And that's important. The pH at the equivalence point will definitely be greater than 7 whenever you're titrating a weak acid with a strong base. So in order to calculate the pH, you have to calculate the concentration of sodium acetate. This is the most complicated calculation. So it's going to be equal to 0.0500 molar. And then you're going to set up an ice table as if I asked you to calculate the pH of sodium acetate. So you're going to have an ice table. You have to calculate the Kb of sodium acetate from the Ka of acetic acid. And that means that you're going to have 0.050 present on the left-hand side and 0 molar on the right. You're going to subtract x and add x, and you're going to have an algebraic expression. You have to calculate Ka from Kw, or Kb from Ka, and Kw And plug those in here, and you get an algebraic expression. So the equivalence point calculation is definitely the most complicated one. You have to calculate KB from KA, so KW divided by 1.8 times 10 to the minus 5, which gives you 5.5 times 10 to the minus 10. Solve the algebra here. You could assume x is negligibly small because KB is such a small number. And then you end up getting an x value that is going to represent your hydroxide ion concentration, because remember, this is a base. Acetate is a base, so it's going to form some hydroxide in solution. So the pH we're going to calculate from the pOH, which is the negative log of the hydroxide ion concentration, which gives us 5.278. Subtract that from 14 to get the pH, and that'll be our point on the graph. So this one is definitely the most involved, the equivalence point of a weak acid titration. 8.72, definitely greater than 7. I feel pretty good. Whoops, I labeled that wrong. That's the strong acid. Oh, I'm sorry. I'm trying to show you here that the equivalence point pH for a strong acid is 7, but of course it's greater than 7 for the weak acid. That will always be true for weak acid titration. And that's because the conjugate base is always basic, because it's a weak acid. Now the points after the equivalence point, the 50 and 60 mils, you're going to have excess hydroxide present, and so the hydroxide is actually going to dominate the pH after the equivalence point. So all you would really do is calculate the excess hydroxide that you have. If you have 4 millimoles of acetic acid and 5 millimoles of sodium hydroxide that you've added, you'll have an excess of 1 millimole of sodium hydroxide. You will have some sodium acetate present, but it doesn't influence the pH as much as the hydroxide does. So the strong base will control the pH. You will determine that you calculate the pOH just from the hydroxide ion concentration, 0.01 moles, divided by the new volume, which is 90 mils. And that's going to give you 1.954, which means the pH is 14 minus that number, which is 12.04. And then 60 mils, or 12.05, depending on how you round 5. Point G is very similar, except that instead of having 1 millimole excess, you have 2 millimoles excess, and the pH is 12.30. So that's why, again, this table is separated into 3 parts: before the equivalence point, at the equivalence point, and after the equivalence point. And again, millimoles, it uses millimoles because those numbers should make more sense than saying 0.004, 0.003. That's kind of annoying to have to say that every time. So it's easier to say 4 and 3 and 2. You guys should get used to millimoles anyway, because if you're going to be a biology major, you're going to use them a lot. So this is another picture that compares titration curves of different analytes that have different strengths. So here it says as the Ka of the analyte decreases. Now remember that Ka, if Ka is large, that's a stronger acid. As Ka goes down, that means as the acid gets weaker, then the flat part of the curve kind of moves up, right? So you can see that where it flattens out, that part just moves up and up and up. And the vertical transition range, where it goes sort of straight up, that part gets shorter and shorter and shorter, right? So for the strong acid, you can see that the vertical part really extends all the way from pH 4 all the way up until about pH 10 or 11. But for the very weak acid, with a Ka of 10 to the minus 10, then you can see that there's almost no vertical part at all, right? It's a very, very small transition. Now there's another example here, titration of a strong base with a strong acid. This would just be the opposite, sort of inverted looking graph, where the pH begins high because the analyte is now a base, and that's where the pH is being measured, is in the flask of the analyte. And then as you titrate it with a strong acid, the pH will of course start to come down. Now, the titration of a strong base with a strong acid will lead similarly to a neutral salt. So for example, if you had sodium hydroxide in the flask and HCl in the burette, you would still end up getting sodium chloride as your salt present at the equivalence point when you've exactly consumed the analyte with no excess titrant, then you would have a pH of 7, just like you do for a strong acid being titrated with a strong base. So, for example, here's our picture with sodium hydroxide as the analyte in the flask, as opposed to it being in the burette when HCl is now in the burette. So you can just as easily titrate a base with an acid as you can an acid with a base. Now, and this is an indication that you see that the pH starts high and decreases. That's how you know that the analyte is the base. This is an example of a weak base being titrated with a strong acid. And again, one of the important points here is that the choice of indicator is very important. If you had chosen phenolphthalein for this reaction, it would have been a poor choice of indicator, because you can see phenolphthalein changes pH, changes color from pH between 8 and 10, and that does not really coincide with the vertical part of the curve. You would be better off choosing an indicator like methyl red that transitions near the equivalence point. It has to be on the vertical part of that transition range in order to be a good choice of indicator. Now the pKa that you see here is still at the midpoint. So the midpoint is still the pKa, and that would be the pKa of the conjugate acid of the base. When we titrate polyprotic acids, you see multiple transition ranges, multiple transitions that are just stacked on top of each other. And so here you see two transitions. There are two equivalence points, or two vertical parts, and then there are two midpoints, right, that they've labeled there at 0.5 and 1.5 moles. And there are a few polyprotic acid titrations that we will look at in lab. And then you could also have a triprotic acid being titrated like phosphoric acid. Now, this is showing you the choice of indicator. If you're titrating a strong acid with a strong base, you could choose almost any indicator you want, because the vertical part of the curve is a very large pH range, and so the equivalence point and the end point will be very similar to each other volume-wise, because the equivalence point, there's such a huge pH range over which there's a very small volume change. However, if you're titrating a weak acid, for example, you see here that the choice of methyl red as an indicator would be not as good a choice as phenolphthalein, which occurs during the vertical part of the transition. Methyl red, choosing that indicator, the end point would be nowhere near the equivalence point, so that would be a bad choice. And again, back to the weak base titration, we already talked about this, that phenolphthalein would conversely be a bad choice here, because it would transition long before the equivalence point, which is down around pH between 5 and 6.